Hey guys, welcome to the matrix multiplication, the next session, which is a part 2 over here. So, just a quick recap, in the last session, what we discussed where we just introduced what is matrix multiplication, and we were just trying to understand what it means to multiply a matrix by just a number, which is also called as a scalar. What happens when a number and a matrix gets multiplied? How does it scales up or scales down, and hence it's called as scalar multiplication. And we used it using a number line, a basic number system multiplication. Then we understood the same thing with matrix algebra, and then we also understood using the vector algebra to just give you a sense of that. And like I said, the beauty of matrix comes in when we multiply two or more matrices together, but scalar is a small part of the multiplication. So let's keep digging more, and let's get into the interesting part in this video of multiplication. And there might be one or two more videos where I'll explain different ways of looking at the matrix multiplication, but the real juice starts in this video. I hope it to keep it very short and concise, so that we can understand and consume what we are hearing. Okay, all right. So now let's understand what happens when we multiply a matrix by another matrix, right? Instead of a number. So let's say there is one matrix A and there's another matrix B, right? Instead of a scalar, let's assume that just a number, which could be like a 3A, right? Where we multiply a matrix A by the number 3. Instead of this, what happens if we multiply two matrices for now? Do not worry about whether it's a 2 by 2 or 3 by 2 matrix. Don't worry about the order for now. Let's assume that there are two matrices A and B, and we're going to multiply that. What happens? So, and let's take an example of real time. What does the multiplication really mean? Because matrix is a natural extension of how a conventional multiplication works. Only thing is it's kind of put in a compact form, and there are certain rules which are common to the way the number system works in terms of multiplication and addition, and there are certain rules which are specific to the matrices, which is what we're going to see today. All right, so let's take a simple example. Okay, this snapshot, I copied it from Domino's. I like Domino's more than Pizza Hut. I just copied it. Okay, so let's say I want to order two types of pizza. One is the veggie and other is the non-veg, right? And for both the pieces, on the veg side I want to make 3 orders, and on the non-veg side I want to make 3 orders, and I put it over here, right? So if you say 3 orders on veg, 1 regular and 2 medium over here, 1 regular and 2 medium, and on the non-veg side again 3 orders of same thing, 1 regular and 2 medium. This is what I want to order, right? And I'm going to order it. Okay, so if you keep the matrices aside for a minute, and if you just focus on this part on the left side of the calculation, let's say they give you a bill on what is the total cost. And if you see here, I've highlighted it. It's not in the matrix notation. It's a traditional bill, right? So how do you typically see the bill, right? You'll have the order entry here, veg, non-veg, non-veg, and then you'll have the size and the order. Like I want to have one order, and what is the cost of one order of the pizza over here, like 75 into 1 and 150 into 2, and then we get the total cost for simply veg. We get the cost for simply non-veg, and we get the grand total of 910 rupees. That's your final bill, right? That's how your bill appears, right? Now let's assume that you're going to slightly change this into a matrix kind of an array format or a tabular format, right? But you'll still have all the details. Normally when you say matrix, like I explained in the first video, it can abstract. We don't need the details. We just need the notation, and the computer will do the magic as long as it follows the matrix algebra. But we are not there yet. We are still going to keep all the details of what it means and the meaning of that. And in the next step, we'll abstract it so that you can understand when we hop or when we slowly abstract, how does the intelligence is retained, but still we can simplify it and just have a play on the numbers, right? So let's work on that. Okay, so this is the matrix notation with no abstraction. That means I'm going to keep all the details of what it is. So what I've done is this whole bill I'm going to split into 3 parts, right? So let's say I'm going to split into 3 matrices, matrix A, matrix B, and matrix C. So matrix A is this portion over here, right? So this tells me what is the veg and non-veg, what are the cost of regular and medium. It's just the cost over here. I'm just abstracting this and this over here in matrix A, all about the pizza details. So let's say matrix A is all about the pizza. Matrix B is all about the orders, right? How many orders I'm going to put. I just have 2 orders. So there are some dishes which is regular, I'm going to make 1 order, and there are medium where I'm going to make 2 orders. Let's assume that that's matrix B, which is all about orders, right? And matrix C is the cost portion of that, right? And over here, we have seen from the simple, this thing, how we have computed, the same thing is going to happen here, right? I'm going to have 1 regular and 2 medium. So I'm going to multiply the regular with 1 and add the medium with the 2, and same way here. And the net cost of this will be still 910 rupees, like what we have the final bill. But this matrix we can call as a cost matrix. I'm not come to the final number yet. All I'm trying to do is I'm just trying to put this whole page over here into a simple matrix notation with all the details of what it is. So what is the details? Matrix A is the pizza, details of the pizza. Matrix B is the details on the orders, and matrix C is the details on the cost. And I have this right now. Okay, so far so good. And the same thing now, what I'm going to do is, hey, the computer does not need to know all the details, because matrix algebra is algebra. Okay, if I'm going to multiply, for example, over here in the earlier example, if I'm going to multiply this and this, it doesn't really matter whether it's a burger or pizza. Multiplication is a multiplication, right? So I don't need the details. I just need to know the nature of the operation. In this case, it's multiplication and addition. Here, if you see, there's multiplication, there's addition, and I just need to know the numbers, right? I don't need to know whether it's a pizza or a burger. So now let's abstract. That's called as abstraction. Okay, so here I'm going to just abstract. So let's say I'm going to build a computer program, right? Over here, if you see, I'm just going to build a computer program, and the program does not really care about your details. It just needs the numbers, right? And I'm going to tell the program, hey, I'm going to supply you with 3 matrices, A, B, and C. Okay, A, B, and C. And like I've explained here, I'm going to tell the program, A is going to be the type of the pizza, B is going to be the type of the number of orders, and C is going to be the cost. Okay, and I just tell the program that the first row on the A is going to be your regular. So, but I'm not writing it here because I've abstracted it, unlike in the previous logic where I've written it. I'm abstracted. I'm not writing it. The computer just need to know, okay, what is what. And this is kind of this is the veg, sorry, not the regular, and this is the non-veg, right? So the computer does not really need all the details here and abstract it. So if I remove this, all the computer cares is just give me this A, B, C. I know what is A. I've already programmed what is A. I've already programmed what is B, what is C. The computer knows. The computer just needs the numbers, and it's going to do this operation. A into B is equal to C. Okay, like this is the matrix algebra. A into B is equal to C. Okay, this is another way of writing it. Basically, this means A into B is equal to C. So all these are matrices. But in terms of metric notation, to keep it simple, it's very cumbersome to write this every time, right? So we just keep it A dot B is equal to C, okay? And what we have done in essence here is abstraction, right? We don't have to worry about whether it's a pizza order or a burger or maybe TV or pencil manufactured. We are defining the rules, what is what, and the multiplication is going to happen regardless of whatever is the theme on this word problem, because the multiplication is going to happen on certain rules which we will discuss, and that's what the abstraction means, right? With no unnecessary details, right? So that's what it is. Now let's talk about how the multiplication itself is going to happen, right? So I've copied this whole table here, right? The ABC over here, right? Okay, and what we are trying to understand is we know the total cost of this. So basically what we have done is we have taken this and multiplying with this, and then adding this with this, right? And likewise it is. So if you see here, in essence, what we are doing to just have an intuition, and this kind of, I borrowed it from one of the best videos that I've ever seen, which is called as I think 3 blues and 1 brown. You guys should watch that if you're interested in mathematics, and how the guy in the video, I think his name is Grant Thornton, he uses or maybe I'm misselling the name, but how he uses the visual appeal to all the mathematical problem. It's a great video, people who are curious about that. But people who are wanting just make a quick score, my video should be sufficient for it. So if you see what these guys are telling here, right? So if you see here, so this is matrix A. So assume that this is your matrix A. This is your matrix B here. Assume that this is your matrix B. And this over C is over here, right? So we have that A into B is equal to C, right? A into B equal to C. But if you see here, right, it's a very interesting way to look at what exactly is happening, right? Let's go from right to left. This is the right and this is my left portion, right? So let's go from here to here. What's happening? So let's say we have this AX plus BY, CX plus DY, which is pretty much this, right? This portion, right? And if I have to write this portion into this, right, how it will look like, right? So I have got two matrices, okay, and there is a addition here. So what I'm trying to do is I'm writing this first column, right, as this is 75 and 105, and over here I'm writing the second column, which is 150 from here and 250. And the XY is this is the XY. So I'm writing 1 here and I'm writing 2 here. So this is exactly this piece here matches to this piece, right? So, and if you see, interestingly, this, if you just take focus on this piece or this piece individually, what it is basically doing is it's taking a matrix with 1 column and 2 rows and it's applying a number. So basically this is nothing but a scalar multiplication, right? Scalar multiplication, that's what it is all about, right? Scalar multiplication, and then there is an addition, right? So interestingly enough, although these are two matrices, if there are two matrices where one matrix is in this format followed by another matrix in this format, it basically means that this matrix, the second one, the B1 on the right, is going to scale, the numbers on this is going to scale this matrix on the right, which is matrix A, by a certain number, which is 1 and 2 here. That's what it basically means, right? So if you understand from that standpoint what exactly is happening, we are going to break it down. When I give you the pizza example, it helps you understand what's going on, why certain computations are made in certain way. But if I remove the pizza example and if it's just all about numbers, it's very hard to understand what's happening. But if you apply this concept, basically it's just scaling the numbers in this particular example, right? There is some sort of transformation happening, and the name of the transformation is scaling, which we already seen. This matrix is being scaled by 1 and this matrix is being scaled by 2. Basically both these matrices are transformed and the type of transformation is scaling. One is being transformed by 1 unit and one is being transformed by 2 units, and that they are being added as a regular number, and the final number is whatever the 9, 10 or whatever we saw earlier, right? Whatever is the final cost of the pizza, 9, 10 over here. So that's another way of looking at that in terms of transformation. When you multiply two matrices based on what is the nature of the matrice and what is the transformation itself, where I'll talk about the whole video in the next session, you can imagine that there is some magic happening on the very matrix itself. In this case, the transformation is scaling, right? It's scaling the matrices and then you get the number. And there is a particular sequence how it's multiplied, and that's very important, and I'll explain you in next video why that sequence is important and how this is different from the plain multiplication, where you can, for example, if you multiply 3 into 5, it's 15, and even 5 into 3 in number system is 15. The order does not really matter, but in matrices certain things are different, which we'll talk about. Like I said, matrix is an extension of algebra on common numbers. There are some similarities and there are some stark differences, right? I'll talk about differences, but I just want to give you this intuition. When we multiply two numbers, you know how things are fitting in, where we started from scalar multiplication, how we are bringing it back as a matter of transformation, and what would be the other types of transformation other than scalar, which we will look into the next two videos. But this is where the intuition is. When you multiply two matrices, just keep that you're trying to, the left part of the matrix, the left matrix is essentially transforming the matrix on the right in some format, right? In this case, the transformation is scaling up or scaling down. It could be some other type of transformation like rotation or something like that, which we'll cover. So think about that way in terms of matrix. When the matrix are multiplied, what does it exactly mean, and why this particular method of multiplication is important where we are talking about that. Okay, that's kind of the key takeaway I wanted to just give it here. Moving on, before we close, I've just put another example here. We are taking a 2 by 2 matrix, and then we take a 2 by 1 matrix here based on the order. Here I'm just taking it like a 2 by 2 here and 2 by 2 here. What I've done is to help extend the pizza context. What I'm doing is, let's assume that this particular number of order is for family, and I'm going to order some pizzas for friends also, and there's a number of orders for friends. So I have a matrix A, which is a 2 rows and 2 columns, right? So that's why it's called 2 rows multiplied by 2 columns, so it's called as 2 by 2. And also have a matrix B, which is the number of orders on the pizza, and this is also a 2 by 2 matrix, which it talks about the orders, right, what's happening. And there's a matrix C, which is kind of used for the total cost, how it's computed, right? And the same stuff they have applied, if you see the maths, so what they have taken here, I've given a couple of examples, right? So what they've done is they have taken this first, right, this, and then they applied on this, the multiplication, right, over here. Okay, and then what they have done is they have taken this, like this for example, and again they have applied on this, okay, over here, and then again they have taken this and they have applied here on this number, right? So the C also becomes like a 2 by 2 matrix because we added one more dimension, so it becomes a 2 by 2 matrix here, right? So just like here this will be just one number, right? Over here here we are going to get a 2 by 2 matrix. For example, over here, let's take this example here, right? So I have this exact copy of this, right? I have a 2 by 2, I have a 2 by 2, and I have a 2 by 2. So let's say this is your matrix A, this is your matrix B, and this is your matrix C. So the final answer will be like something of this sort in the matrix, right? What is the total cost? For example, by the pizza type, whether it's veg or non-veg, and by family or something like that, that will be the total cost of here. So you can understand that's how it kind of it's sected. And the way the multiplication works, just like a quick cheat sheet, is if you take this as an example, there are two matrices A and B. One is on the left side, which is A, and the other is on the right side, which is B, right? So what you do is whatever is on the leftmost, whatever is the leftmost matrix, in this case A, you take the row on that. You take one row at a time and you multiply it by the column on the right side of the matrix, which is B, right? So you take a row on the left, column on the right. So row on the left multiplied by column on the right over here, and then you get this number. Oh, if you see here, this one, they put it here, right? And all these images, just as a disclosure, I copied it from the internet, it's not mine, okay? So they have multiplied, they have taken this row and multiplied by this column, right? It's 4 into 3, 2 into 2, and 4 into 7, right? And they got this number 44. And then they have taken the second row and again multiplied with the first column. If you see over here, second row and first column, right, for this number 37, and then this number, right? That's how they multiplied. So row, column, and that's what they do it. In the first example, we didn't have this at all, so it was just one row. So you could have just got this, you would have just got this, right? Something of that sort. That's how matrix multiplication works. You take the row on the left, and then you multiply on the column on the right. And basically what you're doing is the matrix on the left is trying to transform the matrix on the right in certain ways. And what are different types of ways, we'll just check in a couple of next videos, okay? And before closing in, just a quick way of looking at that. If you remember, in the very first session of matrices, in the opening session, I spoke about linear systems and how that was kind of a precursor for the whole matrix and determinants evolution, right? So this kind of ties back to that, right? So if I take linear equations over here, right, this kind of, let's say that there was a word problem about some agricultural problem which started, or it could be any problem where we are kind of going to abstract the numbers from the word problem and put into equations, right? This is equation 1 and this is equation 2. So basically what this is two equations, 1 and 2, and two unknowns, where we have x and y, which are unknowns, and our job is to find an x and y. So we can take this linear equation and we can kind of put it in a compact format into the matrix notation like that, because like I said, solving linear system kind of gave birth to matrix, and eventually matrix had a lot of applications, and one of the applications was an efficient way to solve linear equations. So it kind of went one full circle, right? So I can write this equation, a system of linear equations, which is two equations and two unknowns, into this compact format, which is like, and they are expressed by a, x, and b, which is a is this matrix, x is this matrix, and b is this matrix, right? And what they're calling is, wherever you have the coefficients for this, right, everything has a number coefficient. They call this the coefficient matrix, which is the matrix A. Matrix X, which is like the variables which we need to find, the unknowns. Since it could vary based on the value, it can change the whole dimension of the matrix. It's a variable matrix. And at the end of the day, once you multiply it, we are going to get some constant. So our job is like, we have some numbers on the right, some numbers on the left, and our job is to find the variables which satisfy this equation. That's what a system of linear equation means while we solve it, right? And this is how it's packed in a matrix notation, where ax is equal to b is equal to, if you see the example, this is how you'll get it, right? Basically what it means is each one of them is a matrix, like I told, but we are just trying to put it in compact form. So I don't think this is very important in terms of examination, but the only thing is this kind of gives an intuition how we switch back in one of the critical applications of solving a system of linear equations, which is what most of the examination problems are going to be. How we switch between writing the system of linear equations in matrix form and then solving it. That's what it kind of means. And this is one more example of a different dimension of coefficient matrix, the same stuff here. So this is what I wanted to kind of bring it to you in terms of matrix multiplication from a pure play algebra standpoint. And the next two videos I'll talk about how it differs, what are the striking what are the major differences when we talk about number multiplication versus matrix multiplication, and then and there will be another beautiful video about different types of transformation when we talk about matrix multiplication. Like I said, how one matrix kind of transforms into another matrix, where we just saw a teaser here about the scaling transformation. We'll talk about different transformation, and that will be really interesting for you guys to just get your head wrapped around what is a matrix multiplication. And after that, we'll straight away get into the examination or textbook problems, what you're going to get, which is what most of you will be interested in. All right, more on the next video. Stay tuned, guys.